Hello and welcome to Data Science for Ecologists in R. In the last video, we learned how to use the residual plot to check some of the assumptions of the linear model. Today, we will get to know the QQ plot, which is a powerful tool to check whether the error is normally distributed. But before we look at this in R, let's make sure that we understand what the QQ plot is and how it can be interpreted. To illustrate what the QQ plot is, let's first sample 100 data points according to the assumptions of the linear model. These data points are shown in this plot right here. The black line indicates the true linear relationship, and the error follows a normal distribution with mean 0 and variance 1. The histogram of all errors approximately looks like a normal distribution, which is not surprising because the errors were actually sampled from a normal distribution. The individual values would look like this. For each of these values, we could now determine the quantile. For example, this value is the 5% quantile, which means that 5% of all values are smaller than or equal to it. Similarly, this value is the 95% quantile, because 95% of all values are smaller than or equal to it. Since these quantiles were obtained by sampling 100 data points, they are referred to as the empirical quantiles. In contrast, we can also derive theoretically how 100 data points sampled from the same normal distribution would look on average. The histogram of these theoretical points looks like this. And just as we did with the sampled points, we can assign quantiles to the theoretical points. This results in the theoretical quantiles, which look like this. Since the empirical quantiles are based on the same distribution as the theoretical quantiles, they look quite similar. For example, the highest value of the empirical quantiles is roughly the same as the highest value of the theoretical quantiles. To obtain the QQ plot, which is short for quantile-quantile plot, we plot the empirical quantiles against the theoretical quantiles. We can start by plotting the 1% empirical quantile against the 1% theoretical quantile, do the same for the 2% quantile, and continue to do this up until the 100% quantile. As you can see, the points lie approximately on a straight line. This is a natural consequence of the fact that the empirical quantiles are similar to the theoretical quantiles. Of course, this is only the case because the sampled values actually come from a normal distribution. If we sampled values from a different distribution, the QQ plot would not look like a straight line. Alright, with this newly gained knowledge, let's go to R and look at some QQ plots there. Once again, we start by fitting the linear model for the height of trees and save it in the variable model1. The QQ plot for this model can then be obtained by generating the second diagnostic plot. In practice, we cannot use the true errors in the QQ plot, as we did in our example, because they are of course unknown. Instead, the standardized residuals are plotted against the theoretical quantiles from a normal distribution with mean 0 and variance 1. As you can see, the points lie roughly on a straight line, which indicates that the assumption of normally distributed errors is fulfilled for our model. Let's also look at an example where the assumption is not fulfilled. For this, let's load some new data and fit a linear model to it. If we plot the model variables, we can already see that it does not look like the error is normally distributed. Rather, the error seems to be uniformly distributed within a certain range of values. The QQ plot for the model confirms this intuition. As you can see, the low empirical quantiles are not small enough, and the high empirical quantiles are not big enough to form a straight line in the plot. Alright, after learning about the QQ plot, we should be able to check these 4 assumptions in R. As you probably noticed, these assumptions do not correspond exactly to the assumptions of the linear model as we learned them at the start of the module. However, the assumption of homoscedasticity and normally distributed errors can be combined into the errors follow a normal distribution with mean 0 and a constant variance sigma squared. As a result, we get the 3 assumptions of the linear model as we learned them. That means we already know how to check all assumptions of the linear model. There's just one small thing left that should also be checked when fitting a model, namely that there are no outliers in the data. This will be the topic of the next and last video of this module about linear models. See you soon!